Welcome to the second module about electric potential and electric energy. So as electric fields, electric potentials, electric energy are omnipresent around us. We all know about batteries that have a certain amount of voltage, or we know about 220 volt that comes out of our electric power LEDs, but also we know that, for example, if we have the transmission line, that they have very high voltage and they are kind of dangerous for us. So what is an electric potential? And it's also a sort of abstract concept, so I'm going to explain it to you with the help of an analogy. But before I do that, I first would like to again explain what scalars and vectors are to you, because this is very important to understand well the difference between a potential and an electric field. So a scalar is something that's only a magnitude. In large contrast to a vector, as we talked about last session, it has a magnitude and a direction. And what I find a very helpful example is those two maps of the Netherlands. In one of them, the one on the left, we see a map that shows all the temperatures. And temperature is a clear example of a scalar. Either way it is 16, or in the best case scenario 26 degrees, but it doesn't have a direction. This is in contrast to the other map where there's the wind direction depointed, and the direction of the strength of the wind both has a direction. Is it coming east? Is it coming west? But it also has a magnitude. Does it basically, can we go surfing or maybe not? So these are the difference between a scalar and a vector. Now we get to the slide where I'm going to explain vectors versus scalars for a contour map. And in this case, it is a contour map for a mountain landscape. So in this case, the lines depict the height. So for example, on H1, we see it is at 200 meter, and H2 is at 100 meter. We can calculate all kind of aspects or properties from this map. For example, if we want to know the height difference between position H1 and position H2, we can simply subtract the two, and we get the difference in heights. But if for some reason we like to take a complicated approach, we can basically calculate the slope, so that's the direction, and multiply that with every step we take, and take an integration. So we also get a difference in heights. The opposite is case is present for a slope. So if we want to take the slope, we take the difference in height and we divide that over the distance we've traveled. This is basically a derivative, as we all know. You may start to wonder why I'm telling you this, but there are very interesting analogies to a potential landscape. So in a potential landscape, basically all the different lines indicate different potentials. So if I have a very large ball and I bring it up to a mountain, I will have to put a lot of potential energy, and the kinetic energy I get from that is large. So the same holds for the potential energy that you get from potential landscape. And from that potential energy, you can actually gain kinetic energy. So now if we, for example, from this map, if we would want to calculate a different potential difference, either way, we could simply subtract the potential at location V2, for example, minus V1, and we know what the potential difference is, but we could also take the integral over all the derivatives of E, so the slope of this potential landscape, and multiply that with the distance we've traveled. So that is basically a way to calculate a potential difference. And here, it's interesting to note again that we can get to the electric field by basically taking the derivative to the distance for the potential. And this is not fully correct way to write it, but it will be a few months from now you will know how to do this better. But that is too complicated to tell you right now. Okay, so now we know that the electric potential is basically the integral of the electric field over the distance we've traveled, dr. So if we now look at a specific case where we have charges on top and charges below, and we get the electric field between those, that's what we learned in the previous section, then the potential difference is basically the electric field, the integral of the electric field times the distance we traveled, dr. And in this case, because the electric field is not a function of r, it's simply minus E times d. So this is how we can calculate the potential for an electric field. Of course, we could have just subtracted one potential over the other, but if we don't know that, we cannot do it. This is what we can notice, for example, for a battery. If we have a battery, we can have two ways to calculate the potential difference between the plus and the minus pole. The complicated way would be to take a wire between the minus and the plus end and to walk all the way through that wire, and every time basically measure the electric field and basically would sum over all these fields and calculate the potential difference. However, we can also simply subtract the two different points and calculate that it's minus 9 volts. So what is this potential actually telling you? I also always sometimes get confused. So what is this potential now? So for example, we know again that the potential difference is this integral of the electric field multiplied with the distance. If we again look at the electric field, we know it's basically the force per charge. This is what Coulomb has told us. If we fill that in, we start to see that the potential difference is actually 1 over the charge multiplied F, the force times the distance. And this is what you have seen before in a previous module. We know that that is actually the amount of work done. So from that you can already see it's actually an energy term, and that is what we call electrical energy. So if we go back, then what we see is actually the potential difference. It's basically the energy per charge. So now I always find this very useful. So I take a step back and I realize if I have potential landscape, it is telling me for any charged object what the energy is at that point that I have. So it's really very much the equivalent for an electric field. And of course this may have gone for you a little bit abstract, but think again about the mountain I've showed you. So now this same potential energy landscape, as we saw in this picture, is the same for any charge, but dependent on the charge that I put in there, is it either way 5 Coulomb or 10, the kinetic energy that I can get from that potential energy is different. So with that, I come to the end of this session, and I wish you good luck with your follow-up examples and exercises.